So I'm going to start remaking my old videos. Of course, I don't actually have any old videos since this channel is only 3 months old, but I do have some older ones that I would like to remake. So the first one we're going to be looking at is carbonylation, which, as you would expect, involves adding a carbonyl group, which is a carbon double bonded to an oxygen. So carbonylation is done by reacting carbon monoxide and something else in the presence of a catalyst usually. And decarbonylation is the opposite. It still usually requires a catalyst, but decarbonylation is more likely to happen on its own. So carboxylation and decarboxylation is the same as carbonylation, but instead it's adding a carboxylic acid group in the form of CO2. Carboxylation usually requires a catalyst unless it's a basic metal oxide, in which case it will happen on its own, or pretty much any strong base because carbon dioxide is actually slightly acidic. Decarboxylation sometimes requires a catalyst. That's why you hear the word catalytic decarboxylation sometimes. But it can also happen on its own. Like, for example, acetic acid vinegar, when it's heated in a vacuum or in an inert gas, it will decompose into methane and carbon dioxide. If you don't put it in a vacuum or under inert gas first, it will burn, obviously, because it's not fully oxidized. Now we're going to look at condensation, also known as dehydration, and hydrolysis. So condensation is when a strong dehydration agent pulls water off of two molecules and makes them bind with each other. Technically, dehydration can happen to just one molecule, but it usually involves two molecules being stuck together. Hydrolysis is the opposite. When an ether hydrolyzes, it splits into two hydroxy groups, but when another polar bond hydrolyzes, the hydroxy group will go on the less electronegative atom, and the hydrogen will go on the more electronegative atom. Condensation reactions will happen on their own in the presence of a lot of heat, or when there's an acid and base reacting. Sometimes they require a catalyst. In fact, most of the time they require a catalyst. And hydrolysis reactions sometimes happen on their own, just with water, but more often than not, they require a base or acid catalyst. And here is the oxidation ladder, which is basically just a ladder of different carbon-based functional groups by oxidation state. Of course, in the formulas you see X is any halogen and M is any metal, and R is any carbon-containing functional group. And I'll just explain them to you. So for an alkane to turn into a primary alcohol, you first need to add a halogen, and then you need to react it with a base, because if you try to just oxidize it with an oxygen-based oxidizer, it won't be specific enough and it will just do a random one. In order for a primary alcohol to turn into a secondary alcohol, you first have to methylate it and then add a strong base. A good methylating agent or alkylating agent is like an alkyl iodide or methyl iodide, which is why I showed it there. In order for a secondary alcohol to turn into a ketone, you need an oxidizer that is adequate. Basically, the oxygen in brackets means any adequate oxidizing source of oxygen, because that's pretty much all oxygen does. And the H in brackets is just any adequate reducing source of hydrogen. So you can see that you need an oxidizer to increase the oxidation state and hydrogen to decrease the oxidation state, because hydrogen is less electronegative than carbon and oxygen is more electronegative than carbon. And at the bottom, I just decided to include fire, which is just a runaway redox reaction. It can happen very easily if you're not careful. Basically, you have a not fully oxidized organic compound, and then oxygen does its thing, and then you're screwed. And now we have halogenation, which can happen by a few different mechanisms. Free radical halogenation is when you have a bond with a hydrogen, usually a carbon-hydrogen bond, which gets oxidized into a fluoride and hydrogen fluoride. Alkene and alkyne halogenation is when a halogen attacks a double or triple bond, usually a carbon-carbon bond, and attaches some of itself there to assert its dominance. Abstraction is when a halogen steals hydrogen from a carbon and creates a double or triple bond. This is much less common, but it does happen. So in this case, the X in brackets represents any oxidizing source of a halogen, except sometimes you'll have something like bleach, where you'll have a sodium and an oxygen attached to a chlorine, and then when it oxidizes something else, then you'll have a sodium hydroxide and a chloride of some sort. So it's not like a formula that accounts for absolutely everything, but I think it accounts for most things. Some of the more reactive halogens, like chlorine and fluorine, can support runaway oxidation of organic compounds, but mostly fluorine, as fluorine can support this more than even oxygen, but chlorine, bromine, and iodine, and of course astatine and tennessine, which don't really exist, don't really support runaway oxidation of organic compounds, because you never really see anyone like burning organic compounds in an atmosphere of chlorine, say.